In the second part, we focus on day-night, sunlight, cycles, and seasons. And there are two important principles that you need to understand first. The first one is why distance matters. Distance to the sun. Okay? With increasing distance, the solar energy flux becomes distributed over a larger area, and this is just illustrated here. Okay? So the energy flux per square meter decreases. This principle applies indeed if you compare different planets, which are at different distances to the sun, but it also relates to different locations on Earth. Okay, some are further away than other regions. Okay, this is one important principle. That is one important principle. The second one is about the slope angle. Okay, why the slope angle matters. And what you see a little sketch above my head. That's probably the first thing you look at. Okay. There are regions on Earth which are where the surface is perpendicular to the sun rays. Okay. All right. And there are regions where the surface is sloped. Okay. There's a slope. It's a slanted surface. And if you think about it, you can easily understand that the exposure surface increases for tilted surfaces. Look at that. You have 1 square meter here, and if you look at it, tilted surface is much bigger than 1 square meter. So the tilted surfaces receive a smaller energy flux than non-tilted surfaces. Okay, that's another important piece of information. Distance. Okay, you can see in that sketch above me that there is an increase in the distance. Okay, it's a slight increase of the distance, but the slope angle makes a big difference. What it means is that different regions on Earth receive different amounts of solar radiation. Okay, and that is important. Okay, let's have a look now at the combination of both. And you can express this actually in terms of a formula. And I just want to show you this formula because it links everything that I have talked about so far. Okay, it's a little formula here at the top, which tells you about the heat flux received. And we're only talking about the top of the atmosphere because there's additional features that come into play, like reflection, albedo effects or so. That's why I always refer to the top of the atmosphere. Okay, so you can see here the solar constant. Well, indeed, you have the solar constant, but then there is the function of the distance. Okay? The distance, you have the mean distance, and then you have a variation of the distance. If the distance increases, the heat flux, or the solar flux, or the energy flux decreases. And then you have the effect of the tilt of the surface, which comes into play here in terms of the cosine of a tilt angle. All right. Plus, you have the effect, and I haven't mentioned that, if you're on the other side, opposite to the sun, indeed you have zero energy flux during nighttime. Okay? So this is how you express a formula for the heat flux, receive the insolation And so now you just have to find a way of how to express that, how to project that onto a surface. Do you want to see some distribution? Okay, so that's an important in the understanding of how much solar energy does the Earth's surface receive. And now you have different type of effects that you can link to the way the Earth rotates around the Sun. The first thing, top of the list, is that the Earth rotates, and that gives rise to the day-night sunlight cycle, and you only receive solar energy during daytime, and no solar energy during nighttime. But also the Earth axis is tilted by 23.5 degrees, and that now determines the region which is located closest to the Sun during summertime. Okay. All right. So that gives us the definition of the summer solstice and the winter solstice. Now you can see that during from June 21st and 22nd of June, you have the incoming solar energy is greatest in the northern hemisphere, and essentially the closest distance you get, the closest distance between the Earth and the Sun, you get at the so-called Tropic of Cancer. Okay. So 6 months later, the situation is opposite, where you have something we call the winter solstice on December 22nd. The incoming solar energy is greatest in the southern hemisphere, okay, and that's now the closest distance between the Earth and the Sun is at the Tropic of Capricorn. Okay. So this explains the season, this configuration. Okay, this explains the season. It's not only the distance, it's also the tilt of the surface that matters here. Maybe even more than the distance. Okay? The tilt of the surface matters. And I should have mentioned that indeed the equator, okay, the equator is defined by, well, on average, you get the most average solar radiation. Okay, so that's the average, on average, closest, smallest distance between the Sun and the Earth. All right. So now, based on this, you can actually draw up a map. And the first map that we create, shown here on the next slide, it's actually the hours of daylight as a function of latitude and day of the year. Okay, so it's a little bit busy, this figure here, but you can see day of a non-leap year. Okay, here are the days, and then you have the hours of daylight, and at the equator it's always around 12 hours. Okay, some tiny variations there, but 12 hours, always 12 hours day, 12 hours night. Okay, but it now differs. It depends on whether you're doing in the summertime or whether you're in the winter time, and depends on whether you're in the northern hemisphere or in the southern hemisphere. And there are actually regions where daytime can exceed 24 hours, and this can happen north of what we call the Arctic Circle. Okay, if you're at the poles, you indeed have strictly 6 months of summer and 6 months of winter, and the phases are opposite if you compare the northern and the southern hemispheres. And this already reflects the distribution of the heat flux that you get. Okay? This one is only daylight hour, but it already reflects the heat flux. Let's have a look at the distribution of the daily average heat flux. Okay? The daily average heat flux, which averages out daytime and nighttime features. Okay? Let's have a look at it. It's shown here. So this is the summary of how much insolation the Earth receives at the top of the atmosphere. Okay? Averaged over a day. So let's have a look at the numbers here. The x-axis are the months of the year: January, February, March, April, May. You can see that. And these lines are contours of the energy flux. Okay? The solar energy flux. And you see a dashed curve here, and the dashed curve shows you sort of the maximum, which is above 400 watts per square meter. So near the equator there is a little variation. Okay, there's little variation, but because the slope angle doesn't change much and the distance doesn't change much. Yeah, a tiny little bit or so. And you have something, the number that you can read here is about 400 watts per square meter. And you already notice that it's significantly lower than the solar constant. Okay, it's significantly lower. You know, it's only a quarter of it. Let's have a look at higher latitudes. Let's go into the southern hemisphere. Okay, let's go into the southern hemisphere. Okay, maybe northern hemisphere is more clear to point out what's happening. Let's have a look at the 90 degrees north. Okay, North Pole. During winter, 0. Absolutely no insolation. During summertime, you actually get a maximum of 500, exceeding 500 watts per square meter. You see that? 500 watts per square meter, and then it goes back into the winter. It's the same in the southern hemisphere, but here just the summer is cut in half in this graph. That's why I show you the northern hemisphere. So you know what the surprising bit is? In polar regions during summertime, you receive more insolation compared to equatorial regions. Okay. Why is this? Why do you think is this? Can you tell me why that is? That sounds wrong, doesn't it? Is it wrong? No, it's not wrong. Although you have that tilt angle, you know, in polar regions, the clue in the understanding here is that you receive the solar heat flux over 24 hours, not only over 12 hours. And this one is daily averaged insolation. So in fact, the polar regions receive more daily insolation compared to the equatorial regions. That's fascinating, isn't it? You didn't know that. If your neighbor comes knocking, you can tell him a big story. You will not believe it. Has to watch my entire lecture. Okay. Okay, so let's have a look. There should be another. No. I think I have to add another figure before I continue with part C. Just give me a minute, okay?